Welcome to Math by McCaw. Today, our topic is the set theory. What is a set? A set is a well-defined and distinct collection of objects. We need to be careful about two concepts here, well-defined and distinct. What is that meant by well-defined? It is that a set's elements must be stated explicitly. For example, tall students in our class does not constitute a set, because its elements are unclear. How tall? It depends, right? So, it is not stated explicitly. But, the students taller than 160 centimeters makes a set, because we stated explicitly how tall they must be to enter our set. What is that meant by distinct? It is that a set's elements must be different from each other. In this example, this is not a set, because one of its elements, 18, is repeated twice. A set is generally denoted by an upper letter. Let A be a set. If X is one of the objects that belong to A, we say that X is an element of A and denote by like this. If X is not an element of A, we denote like this. Let's mention about some important sets. The set of counting numbers starts from 1 and stretches into the infinity. The set of natural numbers is the set that starts from 0 and stretches into the infinity. It is like the improved version of the counting numbers, by adding 0. The set of integers stretches into the infinity on both sides. It contains the negative counterparts of natural numbers. The set of rational numbers is the set of numbers like a over b. Here, a and b are integers and b must be different from 0. The set of real numbers are the set that contains both rational and irrational numbers, like the square root of 2. How do we represent the sets? We have seen this before, but let's enumerate our options. First, by curly brackets. Here, we have two choices: either we can list them directly, like in this example, A equals to 3, 5, 7, 9. And B equals to apple, Amy, laptop. This one is a bit weird set, right? But, remember, you can put anything into your set as long as you define them clearly. Or, we define a set by a property. Let's try to recreate A in the example above by giving it with a property. Here, these numbers are odd integers and they are between 2 and 10. So, we can write as integers such that between 2 and 10 and they are odd. Let's try to do this in reverse. Our set M equals to the integers between 10 and 15 and they are even. What are those numbers, 12 and 14? Be careful here, 10 is not included. We can also represent sets by Venn diagrams. They are particularly helpful while working on set operations. In this example, our set contains 4 elements, 3, 5, 7, 9. Let's talk about the cardinality of a set. Such a big word, right? But, don't worry. It only means the number of the elements of a set. Here, in this example, our set contains 4 elements, so its cardinal number, denoted like this, is 4. There are some special sets we need to know about. The first one is an empty set. A set that contains no element is called an empty set and denoted like this. The cardinality of an empty set is 0. The second one is the universal set. It is the set that contains all the objects and denoted by U. The cardinality of universal set is infinite or unknown. The last one is a unit set. A unit set or a simpleton is a set that only contains one element. For example, our set contains only one element, 0.